Hello, my name is Johnny, and let us talk about the different trees of data structure. A tree is a finite, non-empty set of elements. When we say it's a non-empty set, this means the set will always have a value in it. It is an abstract model of hierarchical structure. It means it is organized in order of ranks, and it consists of nodes with a parent-child relation. You can use this in organizational charts, file systems, and programming environments. Okay, this one might seem funny to you. This is very unusual because a nature's view of a tree is normally the roots would start from the bottom and the leaves would go to the top. Okay, but a computer scientist's view is the root starts from up above and that the branches, leaves, and nodes goes down. Okay, the root is a node without a parent. In this case, we have A, and the siblings are nodes that share the same parent. It could be B, C, and D because they share A as their parent, or it could be E and F because they share B as their parent, or I, J, K, or G and H. So, a internal node are nodes with at least one child. It could be A, B, F, and C. And external nodes are often called leaves, and they are the nodes without children. Here we have E, I, J, K, G, H, and D. And then the ancestors of a node is its parent, grandparent, and grand-grandparent. Okay, in this example, we have, let's take I, J, and K. The parent of I, J, and K is F, and the grandparent of I, J, and K is B, and the grand-grandparent of I, J, and K is A. And then the descendants of a node is child, grandchild, and its grand-grandchild. The child of A is B, and the grandchild of A is F, and the grand-grandchild of A is I, J, and K. And the depth of a node is a number of ancestors. So let's count it from here. F, B, and A. So we have 3. The ancestors of I, J, and K. And the height of a tree as a maximum depth of any node. Let's start counting from B, F, and J. We also have 3. As normally we would not start counting from the roots. And then the degree of a node is a number of its children. Okay, so here's what it means. The degree of A is 3 because A has 3 children, B, C, and D. And the degree of B is 2 because it has 2 children, E and F. The degree of C is 2, and the degree of F is 3. Okay, the subtree is consisting of a node and its descendants. It could be C, G, H, or it could be B, E, F, I, J, and K. And the edge the edge is the connecting lines of a tree. This one we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. The connecting lines of a tree like this one. This one. In this example, we have 9. Okay, to clarify that explanation, here's another example. The number of nodes in this tree is, let's start counting from A, B, C, D, E, F, G, H, and I. So overall, we have 9. And the height of this node is 1, 2, 3, 4. Yes, correct. And the root node is A, and the leaves are D, H, I, F, and C. And the anterior nodes are A, B, E, and G. And the ancestors of H is G, E, B, and A. And the descendants of B is D, F, E, G, H, and I. And the siblings of E is F and D. And the right subtree of A is C. And the overall degree of this tree is 3. The general tree. If no constraint or rule is placed on the tree's hierarchy, a tree is called a general tree. Every node may have infinite numbers of children in general tree, and the tree is a superset of all other trees. Well, the previous tree samples I gave you were general. As you can see, this tree can bear as many children as it wants with no restraints. So basically, the general tree is a tree of no rules. Yes. A binary tree, on the other hand, is a specialized version of a general tree. A binary tree is a tree in which each node can have at most 2 nodes. In a binary tree, there is a limitation on the degree of a node, because the nodes in a library, I mean a binary tree can't have more than 2 child node or a degree of 2. The topmost node of a binary tree is called the root node, and there are mainly 2 subtrees. One is the left subtree and another is a right subtree. Well, unlike the general tree, the binary tree can be empty, and unlike the general tree, the subtree of a binary tree is ordered because the nodes of a binary tree can be ordered according to specific criteria. A binary tree search, or BST, is a binary tree extension with several optional restrictions. The left child value of a node should in BST be less than equal to the parent value, and the right child value should always be greater than or equal to the parent's value. A binary search tree is a node-based binary tree data structure which has the following properties. The left subtree of a node only contains keys with lesser than the node's key. You see, if we have 2 datas, 3 and 10, identifying the node lesser than the root is necessary, and it would be placed in the left side, like this one that you see right here. Okay, and now on the contrary, the right subtree of a node contains only nodes with keys higher than the node's key. I mean the root node's key. In this case, we have 10 placed in the right simply because it is greater than 8. And then it continues, the left and the right subtree each must also be a binary search tree. Like what happened here at the bottom. We have 6 as our root, and then we have 4 and 7. And because 4 is lesser than 6, then it's on the left, and so on. And then a traversal. Traversal is a specific in order in which to trace the nodes of a tree. There are 3 common tree traversals in order. The in order is left, root, and right. Here we have left, root, right, then we should go back left, but since we can't go back left anymore, the only choice here is root, and then right again, and then left, and last T is right. The pre-order is root, left, right. Okay, and in pre-order it's root, left, and then left again, because as long as there's left sides that can be seen, it would always prioritize it because of the order. Okay, and then after there's no more left, only then we turn right and then go back to root, left, and right. Okay, and post order, left, right, root. Here. So then post order, this one we do left, right, root, then left, right, root again, and then left again. But this time it's number one. There are a few advantages when using a tree as a chart, like binary and the others. Number one here is hierarchical structure. Trees naturally represent the hierarchical relationships, making them suitable for organizing and representing hierarchical data. This is particularly useful in applications like file systems, organizational charts, and decision making process. Efficient search and retrieval. This one is the binary trees. The binary search trees in particular provides efficient search and retrieval operations. The logarithmic time complexity of these operations makes them ideal for scenarios where quick data access is crucial. Another is sorting. Okay. The binary search trees can be easily used for sorting data in order. The in order traversal of a binary search tree yields elements in sorted order, providing a convenient way to maintain a sorted collection. Another is balanced trees for improved performance. Balanced trees such as AVL trees or red-black trees ensure that the tree remains balanced during insertions and deletions. This results in more predictable and efficient performance for various operations, reducing the likelihood of degenerating into a linked list. Okay, and another one here we have deletion. Efficient insertion and deletion. While maintaining balance, some tree structures allow for efficient insertion and deletion operation. AVL trees and red-black trees, for example, keep the tree height balanced, ensuring that these operations have logarithmic time complexity. Okay, very useful. And decision trees for decision support. Okay, decision trees are a type of tree structure commonly used in decision support systems and machine learning. They provide a clear representation of decision logic, making them interpretable and easy to understand. And then expression trees for mathematical operations. Expression trees are used to represent mathematical expressions in a tree structure. This can be advantageous in evaluating and simplifying mathematical expressions. Another one is graph representation. Trees can be used to represent graphs, where each node represents a vertex, and the edges are the connections between nodes. Trees simplify certain graphs algorithm and make them more efficient. And we also have this what do you call this? Yes, memory efficiency. This one. Trees can be more efficient than flat structures for certain type of data. In particular, hierarchical data can be represented more compactly using a tree structure. And ease of traversal. Traversing a tree can be done in various ways: the pre-order, in-order, and post-order, allowing for flexibility and processing and analyzing the data stored in the tree. Mhm. Natural representation of parent-child relationships are, I mean, the advantages are trees are an intuitive way to represent parent-child relationships, making them suitable for scenarios where relationships are essential, and such as in representing family trees or organizational hierarchies. Okay, you see, there are many advantages when using trees for your charts or something like that. Okay, Thank you, and I hope you learned from my discussion, and goodbye.